I'd like to welcome you to this second day, May 19th, of the EGI Corporate Associate Technical Conference. My name is Milind Dev. I am currently the interim director of EGI. Today, we'll start off with a session where we have a discussion of integration of geology and engineering in unconventional reservoir characterization and production. Then we'll follow that up with a couple of discussions on our carbon management projects. This is basically to highlight the interconnection between the different areas that we have in at EGI. Followed by that, we have a session on a couple of projects on machine learning and data usage for effective management of in different applications. And then we'll follow that up with our work on traditional geoscience exploration that EGI continues to work in, and we'll finish the day with some discussion of applications, some newer applications that we are working on, such as critical minerals, water management, and so on. So with that, I will hand it over to Al Walker, who is our operations manager.
Hey, good morning again. And just like yesterday, we're going to have three sessions or three talks during each of these sessions. Our first session this morning is by Dr. Lauren Bergenheyer. She worked here at EGI when I was here a few years or several years ago, and she's now in the Department of Geology and Geophysics.
Thanks everybody for being here. As Al mentioned, I did my PhD at University of Nebraska in Lincoln, and following that, I spent 3 years at EGI as a postdoc and research professor. And for the last 11 years, I have been in the Geology and Geophysics department as an assistant and now an associate professor. So still at the University of Utah and within the College of Mines and Earth Science. And glad to be talking to you all today about sort of the last 10 or so years of some of the research that we've doing in my research group on unconventionals. I obviously won't get to talk about everything we've done in 10 years, but I hope to sort of tie together some threads and some themes that you can see in our work in our group, which we call the Reservoirs Research Group. I'd like to start with a land acknowledgement. In this photograph I took in the beautiful Salt Lake City area the other day. We're hosting this presentation in the traditional territories of the Goshute, Shoshone, Ute, Paiute, Navajo, and others. And we recognize that many people of various origins have been displaced onto and within these lands. I'd like to acknowledge many funding sources, several of whom are corporate associates with EGI of our work over the last 10 years. I've sort of listed a few funding sources here in alphabetical order. And also a wealth of collaborators in the Geology and Geophysics department. I have a lot of wonderful collaborators at Energy and Geoscience Institute that I continue to work with, at the Utah Geological Survey, Colorado School of Mines. I have a project in Argentina where I have several collaborators there, and some collaborators at Devon as well. And I would be remiss to not acknowledge the people, the amazing people who have been part of this research group over the last 10 years. These are the 15 graduate students that I've been the primary advisor for over the last 10 years, many of whom are now seated in industry positions, actually almost all of them continue in industry positions today. And I think one thing that I'd like to highlight is over the last 10 years as a woman in STEM, I've had an incredible opportunity to mentor a lot of people from underrepresented groups in STEM. And I think this picture really represents that. And I'm really proud of the amazing people and scientists that they've become. It's truly one of the great pleasures of my work. I'd like to also say a little bit ahead of Kerry Johnson, who is scheduled to give a talk in about an hour. My sort of co-collaborator, my partner in crime in relation to the Petroleum Geology program in the Geology and Geophysics department is Dr. Kerry Johnson. And just to highlight, as we move further and further into the future here, we really have had a great track record of industry training and placement from the Geology and Geophysics department. I think over the last 10 years, we've placed something like 60 some students in internships in industry and 40 some in full-time positions. And as part of the work that we've been doing, we were recognized as the 2019 Grit Award winners as a team for contributing towards diversity and inclusion in the energy industry, because many of our advisees are from underrepresented groups in STEM. Okay, so I want to shift now to the technical topics that I know and love, and that's really working in mudstone dominated systems as they relate to being developed for unconventionals. There's a lot of really awesome work we've been able to do over the last 10 years, but it really can be boiled down to one major research objective, and that is to develop improved predictive geologic models of these mudstone dominated successions that allow for science-guided and responsible and economic development or drilling of unconventional resources. I think, given that unconventionals have largely been land and engineering driven, my sort of forte is saying, there's a lot of subtleties in these plays that if we understood and could predict better, would really drive down the bottom line, improve their performance, and make them a much more sustainable resource. And so that's been the tenet of a lot of our research in these different systems. I've worked extensively in the Mancos Shale, in the Uinta, Piceance, and San Juan basins. I have a whole wealth of work in the Lacustre and Green River Formation here in the Uinta Basin of Utah, which actually I won't talk much about today at all. And then the Pennsylvania Permian, the Wolfcamp in the Midland Basin. We've done work there. In the last 5 or so years, I've been working in the Naikin Basin of Argentina, looking at the Agrio Formation, which is the secondary source rock in that, well, tertiary probably in that system. So the tenet of a lot of our work is that, there's obviously a large variation in the types of mudstones that are developed in unconventionals. And however, perhaps geogeologists on the street might call them all offshore marine deposits and sort of lump them together. But in fact, we know that there's a lot of variability. If we just look at the silica clay carbonate ternary diagram, we can see a variation of just mineralogy within these systems. And of course, those have major implications for reservoir quality, hydraulic stimulation, and also hydrocarbon storage in these rocks. So our goal has really been, from an academic standpoint, is to develop meaningful diagnostic depositional models in order to subdivide this broad offshore environment category to reflect the facies heterogeneity that we see in the mudstones. So I'm going to show you a couple examples where we've been able to do this. This is an example where we've been able to develop these depositional models to subdivide the offshore environment. We'll look here at the Mancos Shale in the Uinta, Piceance, and San Juan Basin, where we've examined both sort of the main body, which is the lower Bluegate member, and the Juana Lopez member, and have some publications in sedimentology on those models. But really, when you look at the system, it's what I kind of call a sea of mud. It's very difficult to try and understand what the target might be for a horizontal well. And so these models have really allowed us to narrow in on what those targets might be. If we look here at this model from Aubrey Durrell's work in the Juana Lopez member, we can see the Cretaceous Western Interior shoreline with protuberant delta bodies that reach out into the shoreline. But what we've been able to sort of do is divide the facies into pro-delta deposits, what we call the fringe zone, where there's a mix of deltaic and alongshore processes, and then this low angle offshore ramp where we actually see a lot of transport of sediment out in the middle of the seaway in a variety of directions. So what we call shelf-hole contorites in the Cretaceous Western Interior Seaway. So this is an example of what we can do with sort of a large stack of mud in trying to diagnose different facies and where they come from. In this case, there's pretty different reservoir characteristics depending on what type of facies you might be looking at within the succession. I'll highlight here some of our work in the Wolfcamp D, or the Klein shale in the Midland Basin. And as many of you may know, this is sort of a deep water calciturbidite depositional system. In other words, we have turbidity currents coming off of the carbonate platform shed into the basin. And the cores that we looked at here are on the western edge of the Midland Basin. This is a relatively siliciclastic sediment-starved location. I know there are others that have much more siliciclastic input. But from this model, you know, the older models really simply just showed a lot of calciturbidite deposition, but in fact, we see evidence for a lot of currents out in the middle, in the medial distal plane, not in the medial basin plane, not out in the distal basin plane, but a lot of evidence for subtle traction currents and contorites and turbidity currents in actually oxic to suboxic conditions, which if you are familiar with the model of the Wolfcamp, really most of the mud has been long hypothesized to be settled out of suspension in anoxic environments. And we simply find that those deposits are the exception rather than the rule within the thickness of this deposit. And then finally, some of our more recent work, we've been looking at the Naikin Basin in Argentina, examining the Agrio formation over a number of years. And the fantastic thing about the Naikin and this really rich oil and gas province is that the Agrio is a known source rock, but it is very thick. You can see for scale here, these are several hundred meters in thickness, these units within the Agrio. Very well exposed. So we're working largely in outcrop, although we've moved into the subsurface now. And this system is really thick. So the question is there really even a horizontal target in this succession, and where might it be? So through doing this, we can see, you know, the Agrio is the youngest source rock interval and certainly less well known than the Vaca Muerta and Los Muelles, but less constrained. And so there's an opportunity to identify horizontal targets here. What we've been able to do so far in this system is characterize the macrofacies at the outcrop level, the thin section, the microfacies, and integrate geochemistry, both XRD and program pyrolysis. And this sort of suite of analyses is pretty typical for many of our studies, whether it's core or from outcrop. And the value of doing this has really been two things. We've been able to develop a new depositional model, whereas previously the center of this basin was sort of just known as a big basinal deposit with suspension settling. You see, we now interpret a lot of contorite currents, hyperpycnal flows, different bottom hugging flows that have impacted sediment transport in the center of the basin. However, the other value of this work has been that we've been able to sort of geochemically screen these outcrops for the most prospective source rock intervals. In other words, here in the center of the lower Agrio that I've shown in a red box, we see that these are actually probably the most prospective source rocks in the system, and they also have characteristics that make them highly favorable for hydraulic fracture. So, you know, taking a thick, several hundred meter thick section and sort of zeroing in on a 40-meter interval that we think is the most prospective is more than academic, and it moves forward the needle in terms of exploration and responsible development in this system. So with this last minute or so, I just wanted to emphasize that we don't just go around interpreting depositional environments of shales in our group. We look at a lot of reservoir quality and migration to assess the play as a hybrid system. We do a lot of stratigraphic correlations. How should we do this? We look at log data and inorganic and lithofacies data to try to optimize them. We look at sedimentary links between sedimentary heterogeneity and induced fracture patterns. And we even do some 3D basin modeling and reservoir modeling of these unconventional systems. And finally, I have a student who's recently finished a study on the Mudstone Diagenesis of the Agrio and how it may impact source and also reservoir quality. This is just a short example here of some work that my student Aubrey Durrell did in collaboration with John McLennan here. And we looked specifically at different expressions of facies in the mudstones of the Mancos Shale and examined how water saturation and also the heterogeneity within the sample impacted fracture propagation. And specifically, we see that fracture complexity and the style of failure changes both with the facies type becoming more complex with the more heterogeneous facies here, but also increases with water saturation. And what we find is that these homogeneous samples behave fairly simply, but in these heterogeneous samples, the fractures are more complex, less quantitatively predictable, and they certainly seem to respond and deflect according to these textural changes. So this is some really cool work that we can do that's quite applied. And then finally, I'd like to just say, moving into new directions, I'll be moving in August. We'll be starting a new Department of Energy project where with Dr. Mike Free, myself, Prashant, Saraswat, and several colleagues at the Utah Geological Survey at EGI as well. We'll be looking to assess the Uinta Basin region, looking mostly at coal, secondarily as oil shale, and looking at trying to evaluate their rare earth element abundance and critical mineral abundance, with the idea that these might be transferred into non-fuel products and carbon-based products, looking at their value. So with that, I'm out of time, and I'd like to encourage you to contact me here at lauren.bergenheyer@utah.edu if you have any questions or concerns or connections.
Okay, thank you, Lauren. I don't see anything out in the Q&A block right now or any hands up, but maybe you could tell us a little bit about that last project. How long do you anticipate that last project you mentioned in the Uinta Basin to be?
Yeah, so the first phase, which we're embarking on in August, is an 18-month funding period for 1.5 million. And I'll be hiring a postdoc for that. And then there is a second phase that we would be hopeful for, that's a 7.5 million phase after that.
Great talk, Lauren. A difficult one to follow up on. Good morning, good afternoon, and good evening. Welcome. My name is Rich Esser. I'm one of the research staff here at EGI under the Carbon Management Group. For those of you attending yesterday's meeting, you heard Brian McPherson present on EGI's carbon management portfolio. He kind of quickly covered the specific projects, a number of specific projects, including the Southwest Carbon Partnership and the Carbon Safe projects. Today, I'm going to go into a little bit more detail on two of those. The SWP project, Southwest Carbon Partnership project in the Anadarko Basin at the Farnsworth Unit, Texas, and the Carbon Safe 3 project in the San Juan Basin of New Mexico. All of the projects, or I should say both of the projects presented here, are funded by the United States Department of Energy and the National Energy Technology Laboratory. The Southwest Carbon Partnership is a Department of Energy carbon capture storage or carbon capture utilization and storage initiative funded to develop carbon management strategies. The SWP conducted 3 distinct phases of activity. Phase 1, from the start of the program in 2003, that ran for a couple years, was effectively a paper study that assessed the region's CO2 sources, transport options, and sink or storage potential. The map on the right here shows all of the major CO2 emitters in the Southwest. Those are the yellow dots, the regional CO2 pipelines, and those are the red lines. And in this case, we're showing the oil fields within about 100 miles of an existing CO2 pipeline. The project also assessed saline aquifers in the region for CO2 storage potential. From there, this SWP transitioned into phase 2. These were the field injection projects. These pilot scale projects lasted for approximately 6 years until the partnership moved to phase 3, which is where we've been since about 2013. Come on forward. Letting me advance for some reason. The arrows don't, there we go. Okay, let's see, we've got a little bit of a lag here. The lag, okay. All right. For the phase 2 projects, the SWP partnered with producers in the region to test strategies at different locations with significantly different geological settings. The Aneth Field project of the Paradox Basin here in Utah partnered with Resolute Energy to inject approximately 300,000 tons of CO2 as part of their EOR process. Some great data on microseismicity came out of that Aneth project. Another EOR project that the SWP worked on was at the SACROC unit in the Permian Basin of Texas. Here, greater than 300,000 tons of CO2 was injected for over 3 years. Kinder Morgan was our partner on that project, and some fantastic simulation and modeling data on CO2 trapping mechanisms came out of SACROC. After this talk, you'll hear Dr. Wei Jia speaking about the Smart Machine Learning Initiative, and that initiative is still using that SACROC model developed by the SWP. The San Juan Basin Enhanced Coal Bed Methane Project was the third CO2 injection study. ConocoPhillips and ARI were the partners on that project. Approximately 18,000 tons of CO2 were injected into a coal seam before the swelling of that coal effectively shut down injectivity. More information on all of these projects is available on the SWP website shown here. The major outcome for the SWD Phase 2 projects was a catalog of lessons learned for the ultimate Phase 3 project, and that's commercial scale injection of CO2. In 2010, the SWP went looking for a partner and a site for this commercial scale injection project. We did start out looking at 2 early contenders here in Utah, one Farnham Dome just south of Price, Utah, and then the Gordon Creek field just west of Price. Both were saline aquifers, pure CO2 storage. At that time, the Department of Energy was urging carbon capture utilization and storage, and that effectively meant CO2 EOR. The partnership found the Farnsworth unit in the Anadarko Basin. The Farnsworth unit was developed in the 1950s, but fairly quickly started seeing a decline in oil production. Secondary water flood was started in the mid-1960s with good production, but kind of steadily declined until about 2010, when the field started tertiary CO2 recovery. The oils being produced from the Pennsylvania aged Morrow sandstone. And here we see a map of the Farnsworth unit scale here for reference. The Farnsworth unit uses 5-spot patterns, and the producer, the operator in the area, gradually built up the 5-spot patterns over time, and then we're going to progress eastward into the remainder of the field. But price of oil kind of put an end to that. SWP started working with Chaparral Energy in 2013 to investigate CO2 injection at the Farnsworth unit. Unlike most of the other CO2 EOR operations in Texas, namely the Permian Basin, or most significantly the Permian Basin, the Farnsworth unit project uses 100% anthropogenic CO2 sourced from the Archelon ethanol plant in Liberal, Kansas, to the north here, and the Agrium fertilizer plant in Borger, Texas, to the south. Among the activities that the SWP conducted at the Farnsworth unit were extensive geologic characterization, including the drilling of a characterization well. A detailed depositional model was developed for the Morrow incised valley sands, and it included identification of at least 8 distinct hydraulic flow units within the Morrow, and that's what we're seeing here, the relationship between permeability and porosity. The characterization data was used to develop a 3D reservoir model to evaluate CO2 storage capacity. Here we're seeing a permeability map of the Morrow, or sorry, the Farnsworth unit. Used to evaluate CO2 storage capacity, storage mechanisms, and enhanced oil recovery optimization strategies. Here we're seeing some of the tracer work that was conducted as part of the monitoring program. The CO2 that was injected was extensively studied and monitored within and beyond the Morrow using a number of monitoring wells, groundwater wells, and a variety of surface installations. The characterization, modeling, simulation, and monitoring data all fed into a risk assessment to better understand the uncertainties of such EOR operations. The SWP has been conducting these activities since 2013 and will continue until next summer, effectively making it close to a 20-year program. In 2017, the Farnsworth unit changed over operators from Chaparral to Petroleum. So what are or were the SWP goals for the Farnsworth unit? Here on the left, we see the programmatic goals for the DOE, at least 1 million tons of CO2 stored, not just injected, but actually stored. That's the DOE's idea of commercial scale storage. Optimization of a number of activities at the site, including engineering, monitoring, and risk assessment. Ultimately, the SWP wanted a blueprint for carbon capture, utilization, and storage that could be more easily applied to other sites in the southwestern US. The table at the right shows the highlights for the Farnsworth unit project, including 92% CO2 storage. It goes without saying that a high priority for any CCS or CCUS project is CO2 containment, and after 8 years of continuous monitoring of surface, groundwater into the subsurface, no leaks have been detected at the Farnsworth unit. Here we see the CO2 and fluid accounting for the Farnsworth unit since the SWP became involved. We're just missing that 1 million tons of CO2 stored mark, coming in at about 950,000 metric tons as of February of this year. We're still likely to get to that 1 million ton mark by July of 2022, the end of the project. But the oil downturn of the last 5 or 6 years certainly hasn't helped the operators and project reach that goal. Gun shy on advancing. Here we see the monthly injection and production data for the Farnsworth unit on the left, with CO2 and oil. CO2 here on the left and CO2 and oil on the right. You see the purchased CO2 volumes drop significantly in 2020, but the downward trend in oil production is the result of no new patterns coming online over the past 5 years, again, due to the price of oil. Beyond the economics of enhanced oil recovery at the Farnsworth unit, the operators are becoming enticed by the 45Q tax credits. Brian again touched on this yesterday in his talk. And the current operator of the Farnsworth unit, Petroleum, is no exception. The partnership recently assisted Purdue with their EPA monitoring, reporting, and verification plan for the field. The plan included all of the MVA activities that were conducted since 2013 as evidence of CO2 efficacy, storage efficacy, as well as any of the necessary baseline monitoring needed for that 45Q plan. And they are on their way to getting that $35 a ton CO2 storage credit for EOR. Interest in 45Q has certainly ballooned very significantly even in the last year. The Carbon Safe initiative of DOE is, Carbon Safe stands for Carbon Storage Assurance Facility Enterprise, and that's aimed at developing sites capable of storing at least 50 million tons of CO2. EGI conducted a pre-feasibility carbon safe project. It's broken up into 4 phases. Phase 1 is pre-feasibility, phase 2 is feasibility, phase 3 is permitting, and phase 4 is construction. EGI, the phase 1 project at the Hunter Power Plant in central Utah, was conducted a few years ago. We did apply for a phase 2 project there at Hunter, but we weren't awarded. In 2019, Enchant Energy partnered with New Mexico Tech to pursue carbon capture and storage opportunities and operations at the San Juan Generating Station, that's pictured here, with storage in the San Juan Basin. That's pure saline storage. It's a approximately $17.5 million project. And they're performing extensive characterization of the site and ultimately preparing an EPA Class 6 permit. This is critical for Enchant Energy and its partners to get a $50 a ton tax credit. That's the tax credit for saline storage. More information about the San Juan Basin Carbon Safe project can be found using this URL here. Here you can see the partners on the Carbon Safe project. Some of the key attributes of the project are the San Juan Generating Station capturing at least 7 million tons of CO2 per year. That CO2 will be transported via pipeline to the central San Juan Basin for storage in the deep saline aquifers. That's mainly the Entrada and Morrison sandstones. The oil and gas interests in the San Juan Basin are generally controlled by, or used to be controlled by ConocoPhillips, but Hilcorp is the major operator there. Hilcorp is a key partner on the project. Characterization of the area is well underway, and the project plans to drill a stratigraphic test well sometime in July or August. Come on, advance. Here you see a map of the central San Juan Basin with the San Juan Generating Station here. The storage complex area is here, and this is where the stratigraphic test well will be drilled. EGI will be assisting with almost every aspect of the project, from fault characterization to model development to risk assessment, and really ultimately development of that Class 6 permit. So in closing, the SWP and Carbon Safe projects, as well as all of the other CCS and CCUS related projects that Brian talked about yesterday, that the team has conducted over the past 14 years, leaves EGI very well positioned to provide the assistance to navigate an ever increasingly carbon managed economy. And that's where I will end. Thank you very much. And I think I'm over my time, but maybe I answer some questions later on this session.
Actually, Rich, you have 15 seconds left. So I don't see anything in the Q&A box here, but I just wanted to ask you one question. If you could elaborate just a little bit about the safety of the Farnsworth unit. There were no surface leaks after 8 years, and you did extensive monitoring. Could you tell us just a little bit about the monitoring efforts that you made for both the surface and groundwater?
Sure. Surface monitoring was conducted. We had several methods. We used soil gas flux monitoring conducted quarterly. We also had an eddy tower, 2 eddy towers deployed at the surface, monitoring CO2 and methane flux continuously for a couple of years. We also extensively monitored groundwater wells, irrigation wells in the area. The Oglala Aquifer in particular is a very significant aquifer there. So we monitored that for not only CO2 leakage, mostly changes in pH, but also heavy metals. But we also looked at hydrocarbon leakage, and we conducted a lot of tracer injections, both aqueous phase and vapor phase tracer injections. The vapor phase tracer injections help monitor the CO2 plume movement in the subsurface, both within the injection reservoir and beyond, including leakage to the surface. And then the aqueous phase tracers monitored the water injection in the Morrow, the injection reservoir, but also in the USDWs as well.
Okay, great, thank you. Good morning, everyone. My name is Wei Jia. I am a research assistant professor in EGI. My background is reservoir simulation, uncertainty quantification, and risk assessment for the geological carbon sequestration. Recently, I have shifted part of my focus on machine learning. So in the next 10 to 15 minutes, I'm going to give you a very short overview of our work with the science-informed machine learning in carbon sequestration. While the bulk of this presentation is about applying machine learning for carbon sequestration, I think some of the experience can be applied to a broader range of subsurface activities. So this presentation will have three sections. Firstly, overview of the SMART initiative, followed by two focused projects that EGI and the University of Utah are working within the SMART initiative. That are the rapid forecast updating from monitoring measurements and active reservoir management in CO2 storage. So the SMART initiative stands for Science-Informed Machine Learning to Accelerate Real-Time Decisions in Subsurface Applications. It is a 10-year multi-organizational effort supported by the Department of Energy and the National Energy Technology Laboratory. Its goal is to transform interactions within the subsurface and significantly improve efficiency and effectiveness of field-scale carbon storage and unconventional oil and gas operations. The three goals of this initiative are to, firstly, employ creative approaches to enable real-time visualization of key subsurface features and flows. And secondly, virtual learning for rapid prediction of reservoir behavior. And thirdly, real-time forecasting of actively managed carbon storage systems. Before we dive into the details of the SMART initiative, let's take a look at the evolution of driving safety and the role of machine learning in that process. Traditionally, new drivers have to learn to drive by physically driving a car, a real car, and their safety can only rely on the passive safety systems. However, with the recent advances of computing power and the machine learning techniques, it becomes possible for new drivers to learn to drive through the virtual learning, like the VR, and their safety can be protected by sensors and algorithms, and even better, self-driving cars already being tested in a lot of the cities worldwide. This similar approach could be applied to the subsurface. The traditional approach could be improved or replaced by a transformative approach that utilizes fast computing, a lot of sensors, and the machine learning techniques. Therefore, the focus of the SMART project is to study how can machine learning transform subsurface operations by addressing four key problems that are the speed, cost, automation, and risk assessment. And during the phase one of the SMART initiative, these research questions are being addressed in different tasks by experts from institutions and national labs. Our team at EGI and the University of Utah is working on two critical tasks that are task 4, real-time history matching and forward modeling, and task 5, active reservoir management for carbon storage. So the first sub-project we are working on is the rapid forecasting using monitoring measurements. The goal is to identify, evaluate, and integrate machine learning techniques with potential to improve the current approaches for rapid CO2 and pressure plume forecast updating from monitoring measurements. The expected outcome is transforming the conventional modeling and simulation workflow to support real-time decision-making for CO2 storage site operations. To accomplish these goals, we focus on 5 key components in phase 1. Those are classifying and defining the problem, acquiring and processing data, measurements integration, selecting the right machine learning algorithm and modeling the problem, and finally ensemble evaluation of VOI, that's value of information. In other words, phase 1 is proof of a concept stage, and we hope to deploy this developed workflow and platform on field site tests with industry partners in phase 2, which will be next year, 2022. The data set we used for the phase 1 work is an associated storage site, the SECROC oil field in the Permian Basin in Texas. The SECROC unit was discovered in 1948. The tertiary production with CO2 injection started in 1972. It is the oldest CO2 EOR project in the US. It is also one of the study sites of the SWP project phase 2 that Dr. McPherson and Mr. Esser had introduced earlier. The SECROC unit was used for many CO2 storage related research, such as the CO2 storage mechanism analysis and uncertainty quantification analysis. As a result of the SWP research carried out almost a decade ago, the EGI team has compiled a hybrid database of real-world monthly data from site monitoring and synthetic data generated by reservoir simulations. After we had confirmed the dataset, we performed the well pattern analysis. In particular, we separated the wells into 3 different categories. The ones in the corners and have 2 neighboring wells. The ones on the sides, those have 3 neighboring wells, and the rest of the wells that have 4 neighboring wells. And then we built stacked long short-term memory networks for the wells with monthly data as an input. Using this LSTM network, we are able to predict the well rates for each well in those 3 categories with a good, pretty good accuracy. For example, figures on the right here show the results for one of the wells. Both the training and testing predictions are very close to the actual data points. So the red line is the training prediction, and blue line is the testing prediction, and the green circles are the actual data. Currently, we are developing machine learning techniques to expand this prediction from only temporal format to both temporal and spatial. The other sub-project we are working on is active reservoir management. The fundamental question we are trying to address here is how can we overcome the lack of relevant experience among CCS stakeholders? While oil and gas industry has learned through doing over the past several decades, there is only few commercial scale CO2 storage deployment worldwide. However, on the other hand, to make carbon neutral or zero carbon happen in the next decade, commercial scale CO2 storage has to be accelerated, and it will be very helpful to adopt transformational approach, learning before doing instead of learning through doing. So the goal of this project is to enable a virtual learning environment for exploring and testing strategies to optimize reservoir development, management, and monitoring prior to field activities. And similar to the real-time history matching project, this project also focuses on deliver a proof of concept by the end of phase 1. We are working on developing a platform with this interface shown here to allow users to gain intuitive understanding of CO2 storage at a user-defined site in an interactive way. And here we choose the carbon-safe Utah dataset as one of the models for this work. This project is also based on a previous DOE funded project that Mr. Ashley just mentioned in his presentation. The map shows here, it shows identify the CO2 storage site. It's a Drunkard's Wash here, located in Colorado Plateau in central Utah. The Navajo sandstone was identified as the primary storage formation. Based on this geological data, such as well logs and Lexi 2D seismic lines, we developed a geologic model and the reservoir model for this storage site. Two important factors in virtual learning or any type of VR related applications are responsive speed and accuracy. While some machine learning methods generate a very high accuracy predictions, such as those deep learning methods, they are usually also computationally expensive and need more time to provide those predictions. On the other hand, some simpler machine learning methods run much faster, such as those tree-based models, but they have some compromise in prediction accuracy. And one critical work we are doing here is to find a delicate balance between the speed and accuracy, and to provide the optimum solution for the virtual learning of pressure and CO2 plume. The figures on the right are example results of the tree-based models we tested on the carbon-safe Utah dataset. It is hoped that this work we performed in phase 1 will be applied to a field projects to help with the operation design, permit application, and other issues. And finally, I want to mention that we are preparing the SMART phase 2, during which we will validate and deploy the method we developed in phase 1 to field scale projects. So if any of the EGI CA members are interested in this project, please feel free to contact me. With that, I'll stop here, and thanks for your attention.
Okay. Do I need to do anything in particular to advance slides? Oh, there we go. Okay. Hi. Thanks to EGI and to all of you for this opportunity to speak to you. I'm Kerry Johnson. I'm a professor in geology and geophysics, and I also wear the hat of Associate Dean for Research in our college. I'm going to give a brief overview of what's happening in Geology and Geophysics department here at the U. And then I'll spend the bulk of my time actually talking about my research and the Rocks to Models Consortium. So Geology and Geophysics is the largest department in our college with over 30 full-time faculty and a robust graduate and undergraduate populations as well. We are an incredibly diverse group, best described as an interdisciplinary earth science and engineering department. Some of the key overarching programs, perhaps of most interest to this group, include Earth history and paleontology, geochemistry, and sedimentology and stratigraphy. We also have a very active surface process and hazards group, including a fully accredited geological engineering degree program, and a longstanding and well-known solid earth geophysics program, including the University of Utah seismograph stations, which is a major regional earthquake monitoring network. So with the seismograph stations, our department's grants only proposals and expenditures are around $5 million a year. So I know Lauren talked a little bit about our energy and petroleum programs. We offer both a curriculum, the Petroleum Industry Career Path, or PICP, and this program has historically fed a robust recruiting relationship with multiple companies. A significant proportion of our alumni have gone into the industry over the years. Somewhat tied to that, we have an active AAPG student chapter offering lectures and exciting field trips around the world, as well as some activity in the IBA program through AAPG. And finally, there are a number of faculty doing energy-related research, but Dr. Bergenheier and I are probably the main folks in geology and geophysics leading that, both of us with an emphasis on stratigraphy, albeit with some different focus. So to explore that part a little bit further, yeah, let me go back one. Oh, maybe I can't go back.
You can use the arrow keys on your keyboard.
Ah, thank you.
No worries.
A little bit of background on me. I have been at the U for 18 years now, and I came here by way of Northern California, Minnesota, and originally from Texas, where I was born and raised. My interests are in siliciclastic sedimentology and stratigraphy with a basin analysis and basin modeling focus. And I'm well represented by my awesome research group shown here from a recent Zoom meeting. I've worked for 25 years now in basins all over Asia, and I have since added Southern Utah and South Africa to the list through my Rocks to Models consortium. And that's what I would like to focus on from here on out. I did it again. So in 2012, I started the Rocks to Models Research Consortium with Dr. Lisa Streit, who is at Colorado State University. I am currently the sole PI on this, although she and I do still collaborate when we can. Over the last 14 years, this consortium has been supported by Chevron, ConocoPhillips, Hess, Shell, and Statoil, with a little over $2 million in funding. The original idea with Rocks to Models was that we wanted to build a database of outcrop analogs for predicting and characterizing subsurface reservoirs. And that includes both qualitative and quantitative approaches, as well as modeling work to guide subsurface interpretation at reservoir and field scales. It also includes some larger scale implications for sedimentary basin dynamics, such as source to sink analysis, signal propagation, and provenance analysis. Keep doing that. So Rocks to Models focuses on linked non-marine to shallow marine depositional systems. We, of course, take advantage of superb outcrops throughout southern Utah, particularly the Cretaceous Western Interior Seaway deposit shown in green on the map in the upper left corner. And especially we focus down in the Grand Staircase, which is where the upper panel is from. Environments shown here range from offshore marine to braided fluvial, with everything in between: barrier islands, deltas, lagoons, estuaries, and shore faces. Recently, we've moved up to focus on some deltaic deposits in central Utah, and in the Karoo Basin in South Africa, Permian Triassic deposits, and that's what's shown on the bottom. And in that case, we're looking at some progradational shelf edge delta systems, and spectacular slump deposits are featured in this photo. You can make these out as dipping surfaces from upper right to lower left with that are comprised basically of imbricated boulder-sized slump features. So our methods include a suite of traditional SED-strat approaches, but with the development of software to support drone-based photogrammetry, the real focus now is on creating true-scale, high-resolution digital outcrop models, photorealistic. And both of these photos on the bottom are actually just screenshots from some of our models. The models have a number of advantages, but in particular, this has really supported the development of large quantitative databases cataloging geobody architecture, including size, shape, connectivity, etc. So highlighting that, we basically create and then mine those databases for a number of outcomes and applications, such as facies proportions, net pay maps for different depositional elements, etc. And all of these are used for predictive reservoir characterization by our supporting companies and modeling in subsurface reservoirs from similar analogous depositional systems. We've also started to incorporate direct comparison from modern environments to look at process-based morphodynamics and scaling factors for better prediction as well. And some of our work on barrier island systems is highlighted in that sense in the lower right, where we're comparing dimensional analyses of modern to ancient barrier island systems as a guide, again, for subsurface prediction. On the reservoir modeling side, we're mainly focused on providing inputs for a variety of modeling approaches, and we found that these outcrop models are remarkably useful for capturing centimeter scale heterogeneity, even over very large kilometer scale outcrop panels. And the main goal here is to actually work with modelers in the companies to incorporate our data for direct business unit application. So let me go down. See if I can get this to play. Right, so our work on turning rocks into models continues. This is the same objectives list that I showed you before, outlining kind of the main goals of our work. The video is showing one of our models from the Panther Tongue Delta of central Utah. And essentially we are panning up depositional dip and looking at lateral facies changes within a river dominated delta system. You're looking at, sort of the transition from distal delta front to proximal delta front to delta plain eventually as we move up dip. Looking towards the future, we have not run out of rocks to work on, quite the contrary. There are a number of different directions that this work could go, ranging from different field sites to applications expanding into carbon capture and reservoir analysis, to exploring some different kinds of modeling approaches, to also some exciting new directions in larger scale basin analysis interest, understanding autogenic processes as a control on reservoir architecture, for example. So I am, of course, at your service and happy to discuss any of this further. I'll end a little bit early, and thanks for your time.
Kerry, thank you very much. That's truly amazing what you're doing there. So I don't see anything in the Q&A right now from other parties, but could you, just maybe expand just a touch on how you've interacted with some of your alumni potentially? I think there's probably some really great case studies there, or vignettes, if you would. Yeah, thanks.
Oh, well, I could tell stories, but no, I mean, historically, 40 to 50% of our alumni in some brackets of years have gone into the industry. And of course, we've certainly felt the ups and downs and ups of various things, but certainly these long-standing relationships, especially with companies like Chevron, we've sent numerous alumni those directions, and they've stayed in touch and moved into some really wonderful leadership positions. We see these folks back on campus for recruiting whenever possible. Lauren and I and the dean tend to make regular trips to Houston whenever we can. A lot of our field trips, we run every 2-year Gulf of Mexico modern depositional systems field trip that usually brings along a couple of alumni with ConocoPhillips. So these are some long-standing relationships that really extend into every part of our program.
Yeah, hello again. My name is Drupad Beti. I'm a postdoctoral fellow at EGI. Today I'm going to talk about the machine learning capabilities that can be applied to understand existing and new geochemistry, pyrolysis, and chromatography data. And this presentation is a precursor to a presentation that Dr. H Satyayama is going to give, in which we're proposing a project. Okay. Oops. Okay. So to put things in context, the classical machine learning algorithms are broadly classified into two. supervised and unsupervised. And supervised machine learning algorithms are usually structured data that have some kind of definition of what the data means. And unstructured, unsupervised data is data that doesn't have any structure or labels. Within the supervised classification, within the supervised machine learning algorithms, we have classification and regression-based algorithms. Classification-based algorithms are the most suitable for conventional pyrolysis kind of system, where we start with input variables which have been measured or attained from literature, and then we end up at kerogen potential determination, kerogen type, producibility, thermal maturity determination. All of this could be derived into a classification supervised model. What this is a subjective interpretation, and each geochemist has a different subjective interpretation standard, which by and large would be the same, but each company would have different reference points to refer to. So what we have done is replaced this hand designed program with a supervised classification model. So as mentioned, the geochemists usually attain the secondary variables by using the primary variables, and then come up with cross plots, and then use the cross plots to come up with the interpretation. What we have done is we replaced this entire exercise using logical algorithms to begin with. So the rule-based or logical algorithm we used to construct to replace the subjective interpretation looks like this. So we start with input variables, and then this is just an example of one output variable. And for this output variable, we see if, okay, the samples have TOC less than 0.5 and S2 less than 0.5. Yes, if that's true, then the data points are to be excluded because the data would be unreliable to interpret, because the S2 peak is so low that the signal could be as equivalent to some kind of noise. And the same is the case with OSI. If the oil saturation index is higher than 150, it is more likely an indication that the S1 peak is has some kind of carryover to the S2 peak, and the data would be less reliable on Tmax and kerogen analysis. So in this fashion, we went on to write a whole rule-based algorithm that a regular geochemist would follow. And the outputs are including data reliability, contamination indicators, quality check, maturity indicators, kerogen maturity, whether it's immature or mature, kerogen type, whether it's type 1, type 2, or type 3 kerogen, maturity phase indicator, if the kerogen is maturity, what phase would it more likely be producing, evaporation losses indicators, and present day or remaining potential. Now, after we have attained these results, we used a supervised classification problem, supervised classification algorithm, which is random forest. And this is after performing multiple, using multiple machine learning algorithms. And we used 10-fold cross-validation. And we finally arrived at random forest with a very good bias and variance. Starting with just the 4 variables, S1, S2, TOC, Tmax, we could attain the following accuracies in prediction, which is pretty phenomenal. So let's say if I had to look at 200 data sets, 200 set of data, and analyze the maturity and evaporation loss, it would take me a minimum of a week or a week and a half. And this could happen once the model is trained. This could happen in less than 5 minutes, because that's the runtime for the algorithm. So these are the kind of machine learning algorithms that we'll be using
to come up with, let's say, MME correction, prediction of organophages, which would be further discussed in the next presentation. So likewise, we could also look at signal anomalies. So this is a regular pyrogram where this is a S1, S2, S3, S4, and S5. And this is an example pyrogram which has signal anomalies. And all these anomalies could be detected using the algorithm mentioned above. We can also look at biomarker identification using the GCMS data. Most of you might be aware that if we use one GC column for a set of analysis, we might have to do a custom interpretation for retention times. In such cases, if we identify what the spectra is and what the molecules we are looking for example, looking at Pristin, Phytin over here, as long as the samples were analyzed on the same GC column, we can come up with a coupled algorithm, a coupled machine learning model with Mass Hunter that can predict the molecules that have been indicated through the mass spectra within no time. So that is the capabilities that I am presenting today, and we are happy to work with individual or group CA projects to understand their data better and make quick on-the-fly decisions. And in the next presentation that follows by H Satyayama, Dr. H Satyayama, we are going to show how we are going to incorporate EGI data that we have curated through Oceans projects since 2013, and how are we going to use that particular data to attain more valuable information on phase prediction, SPI values, and a new indices called gas risk index. Thank you for your attention.
I don't see anything in the Q&A, but I think Milland had a question.
I just have a comment initially. We are showing these capabilities to emphasize the fact that data learning and machine learning, so these type of techniques will become more and more important in making the most of the data that we have, whether it's geologic or engineering or even interpretation. And so these series of talks are basically to highlight our capabilities and some applications in that space. So Drupad, would you emphasize what machine learning does for you that conventional interpretation would not, and then how, and it's important, of course, the domain expertise is important also, right? So what is the role then of a geochemist in using that type of algorithm?
So to begin with, this kind of models cannot, this is not substituting a geochemist, nor is it going to be standalone without any support from the algorithm side. So this is a true amalgamation of both the subjective knowledge and the computational side, because for each geochemist would have a different preference specific to the basin of a behavior that one particular basin is indicating. So let's say if there's one kind of oil-based mud that has been used, that could be incorporated in the algorithm, and then the whole model could be trained again to be specific to get specific information on what the rocks and the results mean for that particular basin, provided the conditions that that particular basin has gone through. So it would need a geochemist informed decisions to direct the model in the direction that they want it to go. And then the model is going to enable them to get quicker, more refined information that would take a longer time for a regular geochemist to reach at if there wasn't a machine learning algorithm present.
Hey everybody, thanks so much for having me. I'm Cody Powell. I'm an assistant professor here at the University of Utah, just entering my 6th year here. And Paula, do you want to introduce yourself?
Yeah, I am a research scientist at EGI, and I'm also a research assistant professor at the Department of Chemical Engineering. I joined in last December in the department. And with
Great.
EGI, I'm there for like 6-7 years. Okay. Yeah.
Thanks, Paula. Yeah, I'm also in the Department of Chemical Engineering, and I came from ExxonMobil as a downstream guy, but doing things in the field of process systems engineering. And so today we're going to talk about data analytics and machine learning in hydrocarbon and other applications. So this is just an overview. So I'll start off talking about machine learning for real-time optimization. We've done some work with thermal power plants where we're actually getting our algorithms online and they're physically controlling power plants. And then Palash will take over after that, talking about production data analysis, machine learning applications in geoscience, and he will conclude for us. So I'm doing machine learning for a lot of different applications. Usually my work is on energy systems and how do you design and operate energy systems in optimal ways. So we use machine learning as a really handy tool to solve important problems. I agree with Drupad that machine learning definitely doesn't supplant actual science and engineering, but these can be really good tools to help better automate systems. So most of my work is focused on using machine learning algorithms in real time to actually improve operations. And we've done applications with live real-time abnormal event detection when you have a big data set. So these algorithms can help to identify when a fault has occurred within your system, and then also help to pinpoint where that fault occurred to help engineers speed up troubleshooting operations. We've also used machine learning to try to provide forecasts for energy supply or energy demand so that we can make better decisions kind of looking forward to the future. We've also dabbled in reinforcement learning to make real-time decisions where you're actually building in optimal behavior into a neural network, and then that neural network is trained to make good decisions based on environmental inputs that change over time. So I'm not going to talk too much about those. The one I'm going to talk about is the one on top, real-time optimization using machine learning models, just in the interest of time. So we are applying some machine learning algorithms live in coal-fired power plants. Real-time optimization, for my days at ExxonMobil, this is a technology that we use pretty ubiquitously, except there, company-wide, we had a team of probably 50 PhD engineers that are spending literally man years, maybe even man decades, building these very complex physics-based process models. Combustion systems are generally too complex. So it's easy enough to model, to do energy balances and model the thermodynamics of the steam cycle side of things. But that combustion process, there's so much going on there that you can model it, but those models are generally too computationally intense to be able to solve in real time to give you any good information on how to operate the plant. Also, this is a much lower profit margin industry, and so they don't have the manpower or the resources. However, machine learning has proven to be a really valuable tool here where you can use something called neural network optimization. So you use these deep neural networks that will map the inputs to the plant. There may be on the order of 100 different inputs that operators would be responsible for changing. But machine learning models can learn the relationships between those inputs and some desired output. And then you use those models to try and figure out, okay, we know the relationships between inputs and outputs. Now, how do we manipulate those inputs to give us our desired output? So we have done a project working with PacifiCorp, our local utility here, where we have used real-time optimization based on machine learning models first to minimize NOx. And we've done this teaming with a software vendor. We have actually deployed these algorithms in a real 480 megawatt power plant. And we observed over the course of about 18 months, we observed about an 18% reduction in their NOx emissions, which was pretty phenomenal. And here in the graph, you can see normalized NOx input plotted against the percent of their total capacity. And you can see quarter after quarter, as those machine learning models get more data and understand the process better, you can see that we're able to drop NOx pretty consistently quarter after quarter. So we were able to spin this project off into a $3.7 million project with DOE, again, teaming with PacifiCorp. And the emphasis of this DOE project is a little bit different. For the NOx minimization, we are using static or steady state models to represent the process. However, over the last few years, there has been a pretty dramatic change in the power generation industry, particularly here in Utah. When PacifiCorp entered this California energy imbalance market several years ago, they saw a dramatic change in the way these plants operated. So this has to do with market dynamics of California, and that is also driven by the large influx of renewables in California. And basically we're seeing above, this is pre-entering that market, and below is after entering that market. This is average generation level, and then the gray clouds are the standard deviation. Actually, these may be 95% confidence intervals. But you can see that pre-energy imbalance market and post-energy imbalance market, the plants are now moving a lot more. So these plants pretty much on a daily basis are ramping from their low limit up to their high limit. And this is happening frequently and pretty drastically. So this concept of steady state optimization isn't going to work nearly as well as it historically has. So we need to develop software tools that keep up. But you can see with the steady state model, you would optimize assuming that the plant is going to stay kind of fixed in its operation. But as the plant moves, that optimal solution that you found is no longer valid. The plant has now moved away from that solution. So we have proposed that adding process dynamics in the model, so that instead of solving for optimal conditions and then holding those, assuming constant operation going forward, you can actually solve for all the steps you want to take over a predefined period and help this plant ramp up and down while staying optimal. The objective here is no longer NOx minimization, but it's actually maximizing the efficiency of the plant. So we want to be able to meet the load while using the minimum amount of fuel. So we are about halfway into this project. We are getting our dynamic machine learning algorithms sort of configured and working. We are doing some work with the actual data. We're using a dynamic machine learning model called the long short-term memory network. And we have been toying around with this in simulation first. So we've developed this offline first principles model of the plant to help us sort of prototype and develop our algorithms. And using that model, we've done a simulation study showing that we think we could do up to 4.6% better by optimizing dynamically than by optimizing just statically. But our real huge objective coming up is how to get this working in an online operational power plant. So in about 18 months from now, we expect to be running these algorithms online and having them actually change the operation of these power plants. So machine learning and getting in this space of data analytics as applied to chemical or energy processes has resulted in a number of pretty high impact publications. So these are some of our recent publications. You could look me up on Google Scholar to see some of the other things my group is doing with real-time optimization and machine learning and sort of energy system analysis and design. I'm going to turn the time over now to Palash.
Yeah, thank you, Cody. I will continue discussion on machine learning application in geoscience. Before that, I will discuss a little bit about production data analytics we are doing at EGI. So can I move the cursor?
Give us just a second.
I'm giving you control right now.
Okay. Yeah, I think I can do. So we have downloaded almost more than 20,000 oils data from Enveras, or previously known as drilling info. Data, all these oils came from all basins, all formations, major formations from USA. They are mainly tight formations or shale. And we have also information about the operators of these oils. After that, we have applied some filters like all oil oils, horizontal oils, and some limitation of minimum number of productions, like 24 months minimum production data. And then we have analyzed those data for different kind of investigations. Like in the left-hand side, you can see we have done production data analysis, or production decline mainly. On the top figure in the left-hand side, you can see in the first year production and the second year production per 1,000 feet of lateral length, or lateral perforation length. And you can see that Wolfcamp, based on 1,048 oils data, performed better than other formations. And the first year production, cumulative production, was like around 22,000 barrel per 1,000 feet of oil. And in the bottom side, you can see the normalized rate. And in the normalized rate, in all four major formations, production decline almost 20 to 30%. That is production decline like 80 to 70% decline. So it is now 20 to 30% of the first month's production after 1 year. And after second year, it is 10 to only 20%. You can see that it is significant drop in the rate. And in the middle figure, we have analyzed the operators' performance. And in the top one figure, in the Eagle Ford, you can see that UOG and Marathon are better than other operators. And in the bottom one, in the Niobrara, Noble Energy and Extraction, they are the better than other operator in terms of the first year and second year cumulative productions. We have also calculated recovery factor, assuming some basic parameters like initial gas oil, initial formation volume factor, reservoir height, and initial oil saturation. We have analyzed around like 10,000 oils from Permian Basin. And you can see that the top figure, that recovery factor is only like 3 to 4% based on these 10,000 oils in Permian Basin. It's very low. We have also applied the reverse engineering to understand the petroleum system in Permian Basin, and we have analyzed like around 2,500 oil wells and 750 gas wells. We have plotted them in various ways, and we have just shown here in few figures like location, longitude, latitude, location, cumulative oil and cumulative gas oil ratio. And we are trying to understand the migration, generation, and accumulation of gas and oil in Permian Basin. And we have some conceptual model also. So my co-authors, Rasul Sarkabi, presented these results in last year ATC, SP ATC. So we have done a lot of data analytics using this production data. However, these are other publications we have, like analysis of North American tight oil production from in AIC journal. But however, we have the data limitations. You can see almost we don't have any data about geologic information like permeability, porosity. We do not have access to those data from public. Of course, we have some idea from published article, but we don't have actual value from any operator or any corporates. We don't have bottom hole pressure data. We do not have fracture spacing or amount of propellant injected during fracturing. We do not have PVT data. So if we provide the corporates if corporates provide us all this data, we can develop better data analytics model. We can develop better machine learning model. So to avoid those limitations, we assume some permeability, porosity, fracture spacing, and we developed reservoir reservoir model and simulated production data. And using those simulated data, we developed a machine learning model. Mainly in our first work, we did simple artificial neural networks model, and we predicted oil recovery, gas oil ratio, gas recovery, and you can see that predicted results are very close to the actual or simulated results. So we published these results in 2018 in journals, and I think 2016 in SP conference. We got a lot of citations in 2 years. And also we have developed that LSTM model for SACROC. My colleague, Dr. Egi already described this model and results in his previous presentation. And so I want to mention few things, like using this LSTM model, not only we predicted the blind test data correctly, we also able to capture the wavy nature or complex nature of this rate. We cannot get all this type of prediction using like normal decline curve analysis like ARPS or Duong's method or any other method or PLE method. So we need the little machine learning model to capture this type of complex behavior. We have some other, we can apply this type of the other things like optimization, field optimization for enhanced oil recovery also. In this example, you can see that machine learning model, mainly known as reinforcement learning that Professor Cody mentioned. We can apply that type of machine learning in EOR or drilling operation. In this case, that there are 2 cases, the machine learning predicted that we should do this type of rate. And as a result, we had higher net present value for this EOR case. We can apply machine learning for other geoscience applications. Here are a few examples. Like first one is segmentation of SCM image to get kerosene, pore content, pore cracks in the SCM image. We can also model spatiotemporal or methane emission for future prediction. We can identify lithophases from borehole images. We can also predict mineral deposit like critical mineral or rare earth minerals from wellbore logs or wildline logs. Finally, in conclusion, I want to say there are numerous applications of machine learning in geoscience and broader areas. And machine learning can do the better characterization without any human errors. And we can apply for them for real-time decision making like EOR, any operational decision. We have domain expert at EGI and University of Utah. We need domain expert to explain the training data first to feed in the machine learning. So without domain expert, machine learning cannot work. Okay. So as Professor Cody said, their team successfully deployed the machine learning application in power plant and operational, really live operational environment. And their team also successfully leveraged the industry and industry collaboration into the DOE funding. We are also looking for this type of project so that we can collaborate with DOE or NSF funding with corporates. So thank you for listening to this presentation. So we are ready. We are happy to answer your question, Professor Cody and me.
Cody and Falaj, thank you so much. It's leave it up to the oil industry to take care of your steady state situation and eliminate it. If you've got questions, please post those to the Q&A. Meanwhile, Milind has a question for you guys.
Again, I would like to make a comment for the audience. Those of you from the upstream industry might be wondering why we are talking about energy systems and power plants. But as you can, as you noticed, we don't work in a vacuum, right? Even field operations, you have surface operations, you have water supply, water disposal, and connected to all of this is the overall framework under which this is operating in terms of, as Cody was pointing out, demand and supply and prices. So all of this is a complex system that has to work in some kind of a coherence. And I think what this highlights, these type of studies highlight, are the algorithms and the expertise that you need in making things work. So I hope that comes through well through these type of presentations. And machine learning in and itself is an interdisciplinary activity, because you need domain experts, as both Cody and Palash were pointing out, and you need computer science expertise in developing the algorithms, and you need people from geosciences, engineering, and even economics working together in optimizing the overall outcome of what you want to achieve. I just do want to point out, though, that the long short-term memory techniques that both Cody and Palash described have not been used that often. So can both of you or either of you talk about what the challenges are in optimizing temporal data, the data that is time dependent, which is inherent in a lot of reservoir applications?
Yeah, I'd be happy to field that question. We're seeing this is sort of the key focus of our DOE project. And I appreciate Milan's comments. My field is really, I'm a systems guy. I know the algorithm side, and I try to use these techniques and algorithms to try and optimize a system. And I think Milan made an excellent point that these techniques could easily be applied across different domains. Our DOE project, and one of the reasons that DOE was interested in it was because we're trying to incorporate the model dynamics. Some of these machine learning methodologies, like neural networks, for example, don't extrapolate particularly well. So when you try to use them in closed loop for optimization, you can get your optimizer starting to explore areas of the model where it may not be as robust, where that you don't have a lot of data in that space. And so you may find that your results get a little bit funky when you start when it starts exploring. So this problem is compounded when you're talking about dynamics. We are dramatically increasing the degrees of freedom, but because we're not talking about optimizing just in this snapshot in time, we're talking about doing this over making many decisions over the course of time in different time intervals. So some of the things we're paying attention to, you actually want your model, or you want your plant to sort of go out and explore this space a little bit. You want it to go in new areas where it hasn't been before, so that you can collect that data and add it into your model. But you also want to do that in a way that's very safe, and you're not risking the operational integrity of your system. So these are some of the things we're trying to do as well. We're trying to take these little baby steps and have the plant gradually explore, but then incorporate also some safety mechanisms where if the plant is starting to move into an area where where maybe operators aren't comfortable with it operating, then you can have overrides. So it's certainly a lot of challenges. Just getting dynamics in there just makes the problem blow up dimensionally, and that makes it harder to solve. So it's definitely a difficult problem we're trying to solve, but we are, as you saw from my slide, we are finding some success there, and we're starting to find methodologies that we think will work.
So I want to add a few points on that. For subsurface engineering, it's very difficult to capture the subsurface flow and subsurface characterization. You can see that this is the final inputs we have selected for this model. But before that, we tried many things for the input. So if we do not connect input with this output, then that is very difficult to predict the output or rates. So it is very important to find out those inputs which can affect the output. So you can see that we have selected like 4 surrounding injection wells bottom hole pressure to predict, and the bottom hole pressure of production data, produced oil, to predict the rate from production. But sometimes if you have faults and some interbedded layers, maybe that surrounding wells will not work. Bottom hole pressure from surrounding wells will not work, because that will not affect that closest production well. So you need some initial screening of the inputs to find out the actual effective input for that output. And sometimes that's difficult. You need like maybe 10 combinations to find out the single one. Yeah, in this paper, we discussed few of them actually.
Okay, great. Good. Okay, thank you very much. Did anybody, I don't see anybody else posting a question on the Q&A box. And are any hands up? So we're going to go ahead and take our break now. We'll come back at 10 o'clock. And now we're going into global issues. When we get back, we're going to start talking about some of the basin studies that have been done here at EGI. So let's all take a break until 10 o'clock. Thank you very much.
Thank you.
There is still a lot to be learned about the thermal regime. And yet we devoted first two phases also to thermal regime. And those two phases were funded by companies listed here. And we also tried to capitalize on the knowledge gained from one-to-one studies, and they were funded by this group here. So first two phases determine that each time when there is a transform continental one linking two rift zones and all three segments reach continental breakup, there would be eventually two initial spreading centers located here. This one would move away and this one would laterally clear along future transform margin. So it would pump its heat into it. And we are not talking about the spreading center itself. We are talking about progressively widening corridor of oceanic lithosphere, which is fairly hot. And in previous two phases, we learned that there are 11 controlling factors in a game, controlling how important is heat transport into the future transform margin is. This is a diagram showing the temperature, and removing one of the conjugates, we can peek into third dimension. So quickly after breakup, there are two very important thermal transients. This one moves away, but this one laterally travels along future transform margin. So there would be a diachronous heating wave, and it would be followed by diachronous cooling wave. So this is thermal regime, which is fairly different from everything what we know from more known rifted margins. And this mechanism, if strong enough, could make up for a lack of prominent rivers, giving us extra burial for our source rocks. The key is now to understand how wide is the zone which is affected. In a case of slow transforms, zone is expected to be wide. And knowledge comes from numerical models we've done 2 generations. In a case of fast transform, zone is relatively narrow. The problem is that one needs to really calibrate this by real data. And it took us a while to find a transform margin, which would have a large and reasonably homogeneously distributed set of penetrating wells to sample, or with some data already in them. So finally, we established connections with Brazil. So we pre-agreed sampling. We already worked out on a subset of wells to be visited in core repositories, 23 to start with. They have the deepest stratigraphic reach. They have suitable lithologies where we would expect sufficient amount of apatite, which we need for apatite fission track and uranium, thorium, helium. thermochronology to understand how wide zone was affected by heat transport from laterally migrating spreading center, and how important is this heating event. And eventually, we don't necessarily need all 23 wells. All we need is 4 reasonably distributed for each of the horsetail structures, and let's say 6 wells for transform margin. On top of being able to do original analytical work on appetites, we either gather already existing data from reports on vitrinal reflectance, Tmax, maybe if they have elide crystallinity, to have another set of constraints for thermal modeling. This phase study is planned for 1 year, starting early next year, and anticipated cost per company is this. Now we can talk about second initiative, which is more regionally constrained, but again, it could produce fairly generic results for applicable to other transform margins. We are talking about offshore Guyana, Suriname, and we are starting a project with its first phase study, which would be devoted to basin kinematic evolution and structural architecture. Structural architecture, we believe, would be the key for understanding the reason for commercial successes, failures, and would help us to predict future prospectivity. And I will try to tell you why. This is free air gravity map, and we are looking at northernmost part of equatorial Atlantic. This is central Atlantic, and this is a little blob of oceanic crust. We will need to do a little bit of a homework on age relationships. We'll need to do a little bit of homework on spreading direction. Wells helping us together with seismic to nail down the oldest age of this oceanic crust. It's not typical Albian equatorial Atlantic crust, it's Caluvian. So it would click here. And what we can do is use G plates for reconstruction and eventually take this piece of oceanic crust, click it with the main body of Central Atlantic oceanic crust, and we will eventually see that this was once southern terminus of one great ocean. And Demerara Plateau would click with the Guinea Plateau. Doing that, we can look at one of the snapshots, Berriasian one. We can see already certain width to the Central Atlantic, and we can see two failed rift zones, which we could recognize in seismics. And now we can go finally to the study area itself, Demerara Plateau, Guyana, and we can box in transform sensu stricto, its horsetail structure. And this horsetail structure is kinematically linking transform into rift zone here. They all achieved Caluvian breakup. We are looking at total horizontal derivative of isostatic residual anomaly map calculated by us in one of our earlier projects. And here we can see 2 oceanic fracture zones. They're relatively wide. They consist of individual ridges. They are imaged by maxima, and the minima image troughs. So we have something like this here. Being in Slovakia means that I have quite a delay, if you wonder why it takes so long. There are 2 stripes of normally thick oceanic crust divided by those 2 oceanic fracture zones, and they're underlined by thinner oceanic crust. So you can imagine what it does to thermal regimes of these. But we will worry mostly about fault patterns here. And this was after the breakup location of initial spreading centers, and they would move out. Spreading vector would initially during the transition from disorganized to organized spreading, it would adjust a little bit, and therefore we have it witnessed, recorded by oceanic fracture zones, these little kinks there. What we want to achieve is something similar what we once did in East India. This is a Coromandel transform, where we could map all its faults and faults of its horsetail structures from 8 large blocks of seismic volumes. We want to do the same for offshore Guyana, Suriname, where we are expecting to see just the easternmost portion of transform sensus stricto and its associated horsetail structure, linking it to Western Demerara rift zone. Here is the snapshot from internet showing incomplete seismic coverage, but being incomplete, it's already incredibly robust. Robust enough to allow us to do very thorough, very robust fault model. Why would one need to do that? Well, for first, to see main tectonic provinces. Here we are looking at Georgetown 3D volume, which is right at the boundary between typical transform related fault pattern and horsetail fault pattern. And we can see the transform here inside of the volume could be split to 6 different strike slip faults, and each of them would have its own displacement dissipation structure. All these horsetail structures would control systems of tiny little pull-aparts divided by tiny little structural highs. So the more we drill into detail, more complicated system becomes. But what it really does, because faulting has different nature inside of a transform sensus stricto and horsetail structure, it controls very different bathymetry, high plateau, transform, and system of ridges and troughs for horsetail structure. What it does with deposition is quite dramatic. Here we are looking at Albian-Santonian strata. We can see that they are fairly thin over the high plateau in a transform sensus stricto area, but their thickness is fairly substantial inside of these subdued topography of a horsetail structure. This horsetail structure actually captured all main rivers entering the oceanic basin here. So delivering a robust fault pattern basically allows one to determine depositional models for distribution of potential source rocks, seal rocks, reservoirs. But also one more thing, which is probably the most important, migration of hydrocarbons. Without all these associated faults, we would be looking at system of parallel separated reservoir layers, and migration would be lateral migration dominated system. But we would have faults, oblique slips, normal faults related to horsetail structures. We would have strike slips related to transform. We would have inhomogeneous compaction related normal faulting, polygonal faulting in pelagic sediments, mudstone dominated ones. And then there would be episodes of gravity gliding, each of them accommodated by own system of faults. Each time when they are in place, laterally dominated migration system breaks down, starts its mixing, and becomes complicated. So we believe that defining very robust fault model could be a good foundation for understanding failures, successes, and a good vehicle towards developing a prediction models for a good targets. The study is again 1 year. We would hope for follow-up phases, obviously. This one would start early 22. In this case, depending on amount of attracted companies, we would recalculate the cost accordingly. Anybody interested in our initiative, I would be happy to talk to you. Unfortunately, I don't see my email here, but I can happily tell you so. mnemcock@egi.utah.edu. Thanks a lot for your attention.
Okay, thank you very much, Michelle. Want to let you know that you provided us with a brochure, but it was too large to put into the chat box. So we will go ahead and provide that to all the participants after this meeting via email. Did you want to talk about your brochure a little bit at all, or bring attention to that?
No, thanks. I think it's self-explanatory.
Okay.
I'm also providing you all with the handouts, which are sanitized versions of this talk, because I couldn't show sensitive data, and brochures are devoted to individual project descriptions. Okay. I would be happy to discuss after interested parties read it and want to analyze it.
Okay, thank you very much. Okay, our next presentation will be by Dr. H Satyayama.
My name is H Satyayama. I'm one of the scientists working for Egi Oceans. I did not put our email addresses, so please. Oh, sorry, I did not copy entire stuff. So please contact us using the email addresses in the chat box. In this presentation, I'm going to present a study on re-evaluation of source rock systems in the South Atlantic, for which we have delivered the report in April this year, and propose a new data science study that Deliverables mentioned in his presentation. In this new study, we are going to use all the data and results from the previous Egi Oceans projects to tackle key issues related to source rock evaluation. Before presenting the South Atlantic study, I would like to acknowledge the 9 sponsors for funding and providing invaluable feedbacks on the South Atlantic project. Egi Oceans Research Initiative started in 2013 with revision of chronostratigraphy, paleoenvironment, and source rock evaluation in the South Atlantic. Then we moved to the Central and North Atlantic with a new workflow enhanced with palimphases analysis, which is a kind of visual kerogen analysis, and allowed us to come up with new indices to compare and high-grade source rock systems in different regions across the oceans. After the completion of Central and North Atlantic study, we moved back to the South Atlantic with this new workflow with addition of biomarker analysis and stable carbon isotope analysis to address issues that we encountered in the previous South Atlantic study. Egi Oceans South Atlantic study included 21 DSTP ODP sites and 20 industry wells in Brazil and Gabon. The Egi Oceans workflow started with data harvesting, followed by data curation and standardization. We also analyzed new samples for organic geochemistry, including TOC, pyrolysis, palimphases, bulk kinetics, biomarker, and isotope analysis. In addition to organic geochemistry, we also gathered data for micropaleontology and analyzed new samples for age interpretation and paleoenvironmental reconstruction. The Egi Oceans workflow is specifically designed to address 2 key issues related to source rock characterization. One is mineral matrix effect. The right graph, HI against TOC, shows the results of rock eval pyrolysis on isolated kerogen samples. So these are the values you would see if your samples are free of mineral matrix. The left graph, again, HI against TOC, shows the results for bulk rock samples. And the red box indicates where you see differences. These differences are due to adsorption of hydrocarbons during the experiment by clay minerals. And in short, mineral matrix effect lowers the HI of samples if they are relatively rich in clay minerals. And that could lead to misevaluation of source rocks. The other issue is classification and identification of organic matter end members. Often you have samples with HI values ranging that of type 2 and type 3. And these samples are usually interpreted as mixed type 2 and type 3, which are gas and oil prone. However, our studies showed that in some basins and in some stratigraphic intervals, such samples actually contain only a small amount of continental organic matter and are more largely composed of slightly altered marine organic matter, which is still oil prone rather than gas and oil prone. So these issues do have strong implications on source rock potential evaluation. And our studies demonstrated that pyrenofacies can solve both problems. With this slide, I would like to show you what differences you will see before and after pyrenofacies and MME correction. So firstly, the average HI values increased after MME correction. And after pyrenofacies, you would get a more detailed classification for organic matter. And these are the examples where your type 2, type 3 mixture samples are actually composed of altered marine. So after pyrenofacies observation, the proportion of marine organic matters increased and source rocks appeared to be more oil prone than previously thought. The pie chart on the right shows gas risk index, which is calculated using phase-specific SPI, so SPI gas and SPI oil. These are the new indices we came up with, and we used them to compare different source rock systems in different regions. For more details on the workflow and these indices, please check Betty et al. In Marine and Petroleum Geology, or actually contact either Drupat or me so that we can send you the pre-proof manuscript when it becomes available online, hopefully next week. And I'm going to highlight the two key issues using the real data from the South Atlantic. The left graph, HI against Tmax, shows that most of the samples are immature. The graph in the middle, HI against TOC, shows a decreasing trend in HI value with a lower TOC, which is a sign of MME, given that your samples are immature. The right graph is a pseudo-Funk-Leveland diagram showing that we have samples type 1, type 2, type 3, with quite many plotting between type 2 and type 3. So I hope that I have demonstrated the importance of checking the presence of MME in your samples and correct for the MME if possible, and having the right or correct classification and identification of organic matter when you study source rock systems. This is the list of deliverables which are available for immediate digital delivery, except for biomarker and stable carbon isotope analysis. With these, we had some delay due to the pandemic, but we have received the results and we are finishing the interpretation. So we are working to deliver these 2 items to the sponsors in early June, if not by the end of this month. Now I would like to move on to a new study proposal that Deliverables mentioned in his presentation. So we would like to propose a new data science study in which we use all the data and results gathered by the Egi Oceans projects over the last 8 years and use them as training set to build a model which can detect and correct for mineral matrix effect and predict organophases or environment and organic matter composition without performing additional analysis such as log eval pyrolysis on isolated kerogen samples. And with these output, we should be able to calculate GRI and phase-specific SPI, and you can incorporate this model into your workflow in your company. As a proof of concept, we run a machine learning algorithm with a small set of input variables, including TOC, HI, the number of benthic foraminiferal species, rock type, rock color, the presence or absence of fine lamination, and the intensity of bioturbation. These are commonly available in well reports. And we use them to predict organophases. For this exercise, we used a surrogate data set with 100 samples. And the algorithm we used is naive Bayes. This is a kind of nonlinear classification algorithms that Deliverables mentioned. And with this data set and algorithm, we attained 85% prediction accuracy. In the new study, we will use, again, all the data and all the results in Egi Oceans dataset, including the pyrolysis results, which have been checked for mineral matrix effect. So we know which samples are affected by mineral matrix effect and which are not. We will refine machine learning algorithm to predict organophases and organic matter composition and to calculate SPI oil, SPI gas, and GRI with higher accuracy. And we think that one of the key aspects of the project is to be able to detect and correct for mineral matrix effect through existing data. So again, without performing additional analysis. And we will start with signal detection that Deliverables mentioned in his presentation. And we will also use other input variables such as clay minerals, compositions, and lithology to attain higher accuracy. This is a broad outline of the proposal. And we would really like to develop this proposal further and make it useful and more applicable to your work. So please contact either one of us or EGI if you are interested. And that's all I have for this presentation.
Well, hello and welcome everyone. My name is Sudeep Kanungo and I've been a research scientist in EGI for almost 15 years now. And I've been working in the chronostratigraphy research division of EGI in the last 8 years through the Egi Oceans research program that Dr. H Satyayama just talked about. Today, I'm here to present a research proposal on the Eastern Mediterranean sedimentary basins, which is the next destination for Egi Oceans research program after the successful completion of the Atlantic margin, more specifically the South Atlantic margin that Dr. H Satyayama just talked about. Let me advance to the next slide.
If you full screen your, there you go. And then you can just use the arrow buttons.
Okay, I think that sounds, okay, great. Thank you, Dustin. So as an introduction, the Eastern Mediterranean, as you all probably know, has become a global hotspot for energy exploration with a strategic location between Europe, North Africa, and Western Asia, connecting as many as 22 countries. This region offers tremendous opportunities, especially for natural gas. And these opportunities were sparked by discoveries that were first made by Noble Energy in offshore Israel and Cyprus in the Levant Basin. There have been many subsequent discoveries in this region, such as the Zohr discovery, the Aphrodite, the Leviathan, just to name a few. The major discoveries in this region are shown here in this map through the red bubbles, both offshore and onshore. And just for your orientation, the Zohr discovery sits right here below the Eratosthenes seamount. And the others you can see are on the right and to the south here. So all these red bubbles, these irregularly shaped red bubbles, are your major discoveries. So as you can see, the potential is huge with more upcoming discoveries. So it is likely that these red bubbles will fill up the map in the near to long-term future. The graph here on the right, top right, shows that there is more than 100 TCF or trillion cubic feet of confirmed natural gas just in the Nile Delta and the Levant Basin. And the curve here shows the cumulative confirmed reserves only in Egypt, including the Nile Delta in the red curve here, the Gulf of Suez in the green, called the GOS, and the Western Desert in the yellow. And the trend, the line that you see in the blue, is the cumulative trend in the region, for Egypt. So what's the big picture here? What are the major exploration challenges? In the Levant Basin, we have a source rock issue. The question remains whether gas here is biogenic or thermogenic sourced, or is it truly a mixed source? This begs a good investigation, starting with the regional synthesis of the area. So the graph here on the left shows you the Tamar field. It shows you the oligomycene source for biogenic gas charging the Tamar field, the Tamar 1 well. On this side, you have the Karish well, which is a possible mix of thermogenic and biogenic source, with the thermogenic source coming from the Cretaceous and the biogenic source from the Oligocene in the Tertiary. And below here, we have the Zohr field, where we can see beautifully captured carbonate platforms in the interpreted seismic profile. But the big question is, are there more of these Zohr-type plays in the region? And do we have analogs for these Zohr-type plays in the region? Next, we'll move to the Nile Delta. You see here an interpreted seismic profile from the Herodotus Basin to the Levant Basin in one figure, in the top right figure. And this shows the oligomycene sequence with the Zohr discovery sitting here right in the middle. You also see the Mycenaean, the late Miocene evaporites or salt in the pink band, which add a level of complexity to the understanding of the pressure regimes in the region. Then below, you see the Western Desert, and the Western Desert has emerged as a very interesting and almost a new region for exploration. The onshore area in the Western Desert has a lot of discoveries, but here you see an interpreted seismic concept through BGS, the British Geological Survey, who've done a lot of seismic work in the region. And you see two major plays here. One is in the shelf area, and the other is the turbidites coming from the Nile region. What remains to be done here is mapping the extension of these turbidites toward the Mediterranean and finding the real connection with the Nile Delta. So this is something that we can attempt to do in our project. So what are we going to do? Well, we are planning a two-phased study approach for the Eastern Mediterranean regional study. Phase 1, which we will start soon, we hope to start soon, will accomplish an original regional stratigraphic and structural synthesis and create a database that will capture the geodynamic evolution of these basins through time. This database will then be used for phase 2, which will answer more specific questions emerging from the phase 1 results at the basin scale and or the regional scale, including some basin modeling, detailed basin modeling. So that's our plan. But the geodynamic evolution of the basins will incorporate visual maps and charts in phase 1 that will be captured in ArcGIS and will include biostratigraphic correlation charts, paleobathymetry maps, GDE maps through paleofacies analysis, TOC, kerogen quality maps, and structural maps such as subsidence and basement fault maps. On the right here, you see an example of a GDE map. It's a simplified gross depositional environment map, something that we can construct in our phase 1. And what you see here is an example where we will use seismic profiles that you see in the faded gray lines that I'm pointing to right now, which will be used to interpret paleofacies along with other data. And then from the paleofacies, we will create depositional environment maps that will capture features like carbonate platforms, turbidites, mass transport deposits, etc. And we believe we can do a much better job than what is shown here. This is a simplified map if we have the right amount of data, if we have the right data with us. So this is an example of a GDE map that we will construct in phase 1 of the study. So what are the tools and available data we have to accomplish the study? So we have here, as shown in the map, we have the EGI database and reports that need to be integrated with literature in the public domain, university publications such as unpublished master's and PhD dissertations, geological survey publications, including samples, logs, seismic, and biostratigraphic data. Here, we strongly encourage company partnerships where companies contribute data to the project with assured confidentiality contracts. The details or source of the data, including the names, locations, and other confidential information, will not be disclosed to the other sponsors, but only the synthesized product and the results will be available, which will benefit everybody in the project, just like what you saw in the GDE map. And let me clarify that a little further. So for example, if a company contributes 2 cores, 2 rock cores to us, we will study them, we will analyze and interpret them, but other partners will not know where the cores are coming from, including their location or other details that are deemed confidential by the contributing company. We will respect that. So you have the data, we have the expertise to analyze the data, and I think together we can make it a win-win situation through a trustworthy or trusted collaboration. This way you can also add more value to the data you have with another interpretation through outside experts, like from EGI. And the deliverables will all be in ArcGIS, so you can use the output in other softwares internally in your company. Collaborations are very important in a region like the Eastern Mediterranean, as you know. We at EGI are experienced and well positioned in developing and forging collaborations worldwide. We have accomplished this through the previous EGI Ocean study all along the Atlantic margin, along the American side, African side, and the European side. So for this project, we intend to focus on academic and research institutions and geological surveys including subject matter experts in the region, especially from Lebanon, Israel, and Cyprus. At this stage, we intend to bypass governments because we know that they can be mutually conflicting when working with some of the countries in the region. We want phase 1 to be a 12-month study starting in the summer of 2021, in June or July of 2021. We anticipate the budget to be in the 60 to 80K US dollar range. And the reason we don't have an exact value is it'll depend on the number of sponsors who join the study. But we would, the minimum number of sponsors would be 5 to kick off this study. And this is where I'm showing our research team, which includes regional subject matter experts like Dr. Fadi Nader, who's an expert in the region and is based in France. He's part of our research team. So with that, I would like to thank you for your attention. We encourage your participation in this important regional study that we are about to embark on. We will be offering personal one-on-one company presentations to your companies. Should that help in convincing your teams and senior management? So we are happy to do that. So please express your interest. We'll be reaching out to you in the next week or so, asking again for you to express your interest in participating in this important regional study. And so thank you. I appreciate the opportunity to speak with you, and I think I'll leave it there for questions if there are any. Thank you so much.
Some of the ideas and services which we have in terms of databases. As you know, EGI has a variety of services, technical analysis, short courses and research projects, and you heard several proposals and initiatives. But one important component is databases. And about 10 years ago or so, EGI developed this data platform called iCords. So I'm going to share with you some of the things which we have done and also the things that we are going to do. So iCords is an acronym, is for Integrated Continent Ocean Research Data System. So this includes database construction, but also we are adding data analytics and also machine learning modeling for various apps. This month, EGI hired a software developer, Thomas Cook, who has almost 2 decades of experience in software engineering and modeling. So we are really very delighted to have him on board. Also, Christopher Kessler, who has been at EGI for many, many years. So he's in charge of geospatial mapping and also GIS systems. Polish Panja, he's a chemical engineering, but also he is doing machine learning, so as well as the EGI scientists. So we are all, together in this venture. So I'm basically coordinating our efforts. So one important component which we already have and we are trying to develop is related to the offshore basins. We have hundreds of millions of data points, wells, geochem, strat, geophysical data, etc., offshore. So we are trying now to create an app for all these databases. By the way, iCords apps, they are subscription-based per year. So that is how you have access to this database and apps. So we are suggesting like 30K annual subscription fee for each app. So this is something that we have lots of data, and if you contact us, we will provide more information. But today, what I'm going to share with you is a new app on critical minerals. mostly supporting energy systems. As you know, this is a very trendy and hot topic. This month, I published one review overview article on critical minerals from sedimentary basins. But the database which we have, we are also including non-sedimentary rocks, especially mafic igneous rocks as well as metamorphic rocks. So again, this is an annual subscription based. So the database which we have been working on, especially in the past 2 months, Christopher Kessler and I have been working on this. So we have created base geomaps, lots of them, global distributions for some of the critical minerals, their lithological associations. We are moving now into geochemical data and also capturing the infrastructure, the companies, as well as the markets. So what I am going to do, I will show a prototype of what we have been doing in terms of an online ArcGIS. I hope you can see. Al, is this visible to you?
Yes, we've got it.
Okay, thank you. So this is the prototype, Christopher Kessler. We have been working on this. This has lots of maps, data layers, and features. I don't have much time to go through all of it, but you have the data layers for sedimentary maps, for example. We are using both USGS sedimentary mapping as well as Robertson Fugros sedimentary maps, which is more commonly used. We have geological base maps showing the rock distributions for the entire world. This is a more generalized picture, but you also have more detailed geological maps, outcrop maps, so you can see the ages as well as rock types for various countries and continents. This is for Africa, for example. Now, we have also incorporated all the USGS databases, which is a lot of data. We have summarized, this is a work in progress. We are looking at distribution of specific rock types which are host to many of these minerals. Now, among them are Precambrian rocks, but also intrusive rocks, as well as mafic rocks. This is where you will find lots of metals. So this is our first attempt, in a way. Let me see if I can zoom in and then you can see better. For example, the US. So this is the distribution of intrusive rocks into the sedimentary basins, as well as mafic rocks, which would give you some idea about the mining possibilities in these areas. The other thing which we have done is adding a layer showing the distribution of minings for specific critical minerals. For example, antimony, you have barite. I don't know if, let's see if it will show. Okay, this will be better. This is, selected sites like barite. You can add, different layers, beryllium, cobalt, lithium. So you have a worldwide distribution. As I said, this is a work in progress. We are trying to add geochem data to this mineral sites. There are also, I don't want to, there are also some gravity maps, for example, aeromags, world stress maps, in situ stress, heat flow data, data on induced seismicity related to both oil and gas as well as mining. So there are lots of you know, data layers that has gone into this ArcGIS 5. We are still trying to digest. This is a huge database from USGS, but we are still trying to digest this just because it's and try to add some geochem data to this database. So in short, this is going to be a huge, huge database, and we are trying to really tailor this towards critical minerals where you can get, you have access to both geology, geochemistry, and also the financial aspects in terms of economy and marketing, etc. Yeah, this is a huge database which USGS put together in terms of minerals. This has like more than 10 million data points, and also the geochem data.
Okay, thank you for attending this presentation. My name is Palas Panja. As I introduced before, I am a research scientist at EGI and a research assistant professor at the Department of Chemical Engineering. So the main objective of this talk is to discuss the potential of thermal storage and associated risk, challenges, and opportunities, as the title suggests. Here is an outline. After a brief discussion on the background of thermal storage, I will show you some results from our preliminary studies, and then I will discuss risk, challenges, and opportunities. So with increased production of the renewable energy, mainly solar and wind, the storage of the electricity is the critical component to become independent from energy from fossil fuel. There are many problems with wind and solar. Mainly wind and solar can generate energy but cannot store. We need large-scale storage system. Also, wind and solar cannot provide on-demand energy. That means in the afternoon and in the nighttime, wind cannot supply energy or electricity. Solar cannot supply electricity. And wind energy is also dependent on the weather, seasonality, and that's why we need some storage component. Here is a famous chart. It is developed by California Independent System Operator in 2013. And after that, they predicted this chart for 2014 to up to 2022. And since then, actually, these curves are not updated, but it's still used for deployment of solar energy. This is known as a duck curve. This is basically the difference between the electricity demand and amount of available solar energy. And this is from the springtime in California, and this is the snapshot for 24 hours data. So you can see in the daytime around like 8 and 9 a.m. to 8 a.m. to maybe like around 6 p.m. the generation or the electricity generation from the solar is huge, and that's why we have less difference and it drops dramatically. And this is known as the potential. This is known as over generation. And that time, if we supply this to the grid, traditional grid, then operator from the power plant like natural gas power plant or coal fired power plant, they don't need to run the plant at their capacity. so they can drop their capacity. But as the sun sets and people start using electricity for lighting or heating at the home, the demand for electricity increases and supply for solar drops because we don't have any sun. So this is double impact on the power plant. So they need more demand and they don't have supply from solar or backup from solar. So that's the problem. They need huge ramp up. So that's the problem. So that's why we need some solution. So one potential solution is thermal storage in porous media. And if we couple this thermal storage system with the solar energy, then we can solve this problem. And you can see in that figure here in the duck curve that excess energy generated from the solar can be stored during daytime in a porous media, and that in terms of like hot water, and that water can be produced in the afternoon, in the night time, and whenever it is required to generate electricity. And it can be also used for seasonal storage. The thermal formation can be used for seasonal storage, and it can be used to produce electricity for all day in the winter time. And that concept is known as geothermal battery or GB. So first of this type of studies is conducted by INL, Idaho National Lab, with collaboration with University of Utah and other groups. They studied two wells system, and they had like two cycles. One is charging cycle. In the charging cycle, they produced cold water from one well, heat it up using direct solar heating like parabolic trap, or heating by electricity over the excess electricity, and inject that hot water into the well. And in the night time or whenever electricity demand is high, that hot water can be produced and electricity will be generated, and that cold water from the geothermal power plant will be again injected to the cold oil. This is the two well system, but there are many other systems I'll discuss later. So for this GB concept, we need a good formation with high permeability, high porosity. We need a thermal insulation on the top and bottom. Also, those top and bottom layers should have a low permeability to minimize the heat fluid loss. There are a few other configurations other than this two well concept. There are like 5-spot concept, horizontal well, and slim well. I'll discuss them later. So at the University of Utah at EGI, we had one project from NSF. John McClellan was a PI. We studied a simple cylindrical model, and in this model, middle is the formation with high porosity, high permeability, and the top and bottom we had overburden and underburden with low porosity, low permeability, and low thermal conductivity or low specific heat. And in the middle, we had one injection oil, one production oil. Basically, it is one oil, and it is used as injection oil and production oil. So this is like half and puff operation. So we injected the hot water at 250 degrees centigrade for 8 hours. You can think about like we injected from morning 8 a.m. to afternoon 4 p.m. for 8 hours. Then we start producing that same water for 10 hours at the rate of 32 kg per second to generate electricity. Then we kept the oil shut in for 6 hours for pressure equilibration. And this operation is like 1 day cycle. You can see that total hour is like 24 hours. So this is repeated for months or few days. So this is a temperature profile with number of cycles. One cycle is basically 1 day. So this is the temperature profile from the bottom hole of the oil. You can see during the injection, the top portion is the injection, the bottom hole temperature during injection, and bottom side of this curve is the temperature during shut-in. And production temperature drops from this injection temperature from the top to bottom during the 10 hours of production. So you can see that during injection, the temperature reaches 250 degree at the bottom hole because the injected water stays near the wellbore. And during the production, temperature start falling from 250 to initially it drops around like 160 or 180. But after 70 cycles, it stabilizes around 230. So it drops from 250 to 230. So we have only the variation of 20 degree, 250 to 230. And we have also calculated the energy recovery or heat recovery. After 20 days, we recovered almost 88% heat. After 40 days, it's 90%. And then it behaves asymptotically. And after 100 days, we recovered almost 93. And 93 is almost like a steady value. And we published these results in last year's ARMA conference. We have also published in Renewable Energy Journal. We have also conducted few other studies like deep layer in the reservoir or multiple layer in the reservoir. We have published few, already we have published a few of these studies. We are going to present in this year ARMA also. So the conclusion from these preliminary studies are like, we have noticed that pressure during the stabilization, during shut-in quickly comes back to initial reservoir pressure. And also we have noticed that there is a small extent that means for our operation, for our injection rate, it was only like 25 to 30 meter from the wellbore radius. We have also conducted sensitivity of the permeability, and we noticed that it is only like 50 milliliters is enough for this type of studies, type of storage. We have achieved 90% recovery in 40 days. And sometimes if you inject hot water without production for 30 days to 60 days and then start the daily cycle, it improves the temperature and also it improves the overall recovery. But there are many challenges and risks. So one of the challenges is to prevent the heat loss to that overburden and underburden. If we can find some suitable reservoir with this insulation, then it can be mitigated. If there is a chance of escaping of hot water in the presence of fault and fractures. Also, there are if there are many interbedded layers, the flow can be restricted between in certain layer. No, it will not go. It will not reach to all layers, and we need sufficient pressure to maintain the single phase because we are using 250 degree centigrade water. There are other problems with minerals dissolution and mineral deposit in the reservoir, in the surface of the pipe or equipments, and there are a lot of surface footprints also. But we have a lot of opportunities. There are numerous abundant oils, but problem is that we may have some problem with trace residual hydrocarbons. We need to study multi-well simulations, or we need to study the well placement and interference. In this preliminary studies, we did not consider like reaction. We may need some advanced simulator like TAF or CMG stars. We need some basic economics, need pilot demonstration. There are three other concepts other than two wells concepts, like 5-spot concept, horizontal well concept, and slim hole concept. So I have like few minutes. I will discuss them quickly. So in the 5-spot, during charging mode, we can produce from cold water and heat it up using solar, and we can inject it back to the hot well. And during discharging, we can use that hot water and produce from there and inject to the cold water. And already we are using the multiple oils drilling from single pad. We can use the same technology from oil and gas, and we can drill multiple oils from the single pad and use them as the geothermal storage system. We can use this type of configuration also. There are many cold oils outside in the peripheral locations. Then in the middle, we have main hot oil where we can produce hot water. And outside of this hot oil, we have some other oils for injection. This is very effective way to minimize the surface footprint. So why does the oil and gas industry fit in this business of thermal storage? So you have oil industry has the skill set, like we are using the extensive drilling for shale or tight formation, single pad drilling. We can apply the same knowledge for drilling in the sedimentary basin for this storage. We have expertise in the oil and gas industry for 3D exploration and modeling for reservoir characterization. And we have also geochemist expert in the oil and gas industry. Same concept, same expertise can be deployed for this thermal storage development. Normally the power plant, the ownership is not held by oil and gas industry, but they can be collaborated with the power plant operators, or they can keep their ownership, but this is a very low margin, long payback period. And thank you. If you have any question, I am happy to answer.
Hello again. As you heard from the previous discussion, there are opportunities to use reservoirs in a passive manner for thermal storage. Alternatively, let's consider, and it's a very popular topic these days, using produced water as an energy source and extracting thermal energy from those reservoirs. Well, we're all familiar with the status quo, of course, for produced water, and this is, you can see this is only 10 years ago. And 10 years ago, we talked about beneficial reuse, but we really didn't consider too much extraction of thermal energy and conversion of that to electricity. So let's sort of consider, what about using produced heat from some of the produced water that we're considering here? And, in truth, this is not a new topic. And there have been some low temperature geothermal applications that are notable that sort of led the way. And so this is not an oil and gas application, but it just shows, it demonstrates that low temperatures are possible. This is the Chena Hot Springs in Alaska. Now, of course, I'm cheating a little bit here because they were able to chill the outlet side to about 4 degrees centigrade, okay? And what counts in these is the differential temperature, and that governs the efficiency of these electrification operations. However, there have been other experiments and pilots in the last decade or so, and the most notable one was at Ramatzi. And Ramatzi was the Rocky Mountain Oilfield Testing Center located in Wyoming. And Ormat, a premier binary system manufacturer, carried out an experiment there about 10, 12 years ago, where they successfully produced about 280 kilowatts of electricity from a binary plant. And so it sort of demonstrated the possibilities for doing this on a local basis. In China, there have also been some pilots where this has been done on a field-wide basis. And this is showing one particular operation with, you can see there's a cooling tower, a heat exchange system. And they were producing, it was a modest amount of electricity, not a great deal, but modest. And what I've seen reports of between 350 and 400 tons per day, and that's about 3,000 barrels of liquid per day. I've also seen published numbers of 18,000. So this can be handling a significant amount of produced water. So what you have is a combination and requirements of you need to put a temperature differential across your plant, and you need to have adequate flow to make this economical. And we'll come back and we'll talk about this a little later. But as you can see from this particular drawing here, and let's just look at the drawing on the left, is that suppose you've got hot water. Now, actually, this says hot water from the separator. Indeed, these days, you can take advantage of co-produced fluids, and you can run oil and water through some of these plants without separating out the water. but you run the water through some sort of a separation, some sort of a heat exchange system, and you can heat up a binary fluid, which has a lower boiling point. That lower boiling point fluid flashes, and you drive a turbine, you condense that fluid, and you recycle it. And so this can be done either in directly flowing fluids from the reservoir, or people have looked at closed loop systems where they have a concentric pipe, insulated concentric pipe, and they pump a cold fluid down the annulus. They pick up fluid from the formation itself and pump and return that heated fluid to the surface for a same type of operation. This is not just going on in North America. There's sort of a longer history even in Europe where people have looked at this, and Vermilion has a couple hundred wells, or is in the Paris Basin and the Aquitaine Basin, and they have used organic Rankine cycle, or they're looking to use organic Rankine cycle turbines, which is basically these binary plants for converting hot water of moderate temperature, low enthalpy hot water to electricity. And indeed, if not electricity, the Swiss have been using these types of systems for direct use and heating. And that's maybe not as directly applicable to oil field operations, but we can consider that maybe there are other applications in a cascading process where direct heat might have some value on location. So let's look at the opportunities. Does this really apply to oil fields in the US? Well, if you start to look at some of the available statistics, and this is from some wells drilled in Texas, and you can see with depth and with temperature that there is some water that has reasonably hot temperature. Conventional rule of thumb might be that a standard organic Rankine cycle plant can easily operate at 150 degrees centigrade. But what we have found with newer developing technologies is that these technologies, with improved conversion systems and improved refrigerants being used in these systems, can produce electricity where the wellhead temperature is much less than that, and in fact less than 100 degrees centigrade. With some loss in efficiency, but the utility of these systems is improving as we speak. And so there is an opportunity for definitely converting existing wells that are sort of reaching the nadir of their productive hydrocarbon cycle, and extracting temperature from the produced fluids. You can be co-producing oil and water and heat. And people are also looking at other utilizations of waste heat, for example, from flaring, possibly from compressor stations. And as I said, sometimes there are opportunities depending on the proximity of energy users to use direct utilization, like heating and cooling, and combining it with heat pumps, for example. So it's a whole different dimension. And it's an investment that is possible to make. You know, there are some requirements. You know, we need to be realistic about this, but there are a lot of opportunities too. You need to have a nearby market. You can't be transporting heat long distances. Otherwise, you're going to be using insulated flow lines and losses and expenses that you don't want to be making. As I have indicated earlier, you need to have adequate temperature and adequate temperature drop across these devices, as well as a flow rate. And to reach reservoirs with these temperatures, you know, it's well within the range of drilling technologies that we're commonly doing, and there are many wells that are available for using this. And so some of these, you may have to remediate the wells, and that may be an expense you may or may not be willing to take on. Also, there are lift requirements, and in terms of this, those parasitic losses always have to be taken into account in your overall economics. But they can indeed be favorable. You need a sustainable rate, or you need a portable device that can be moved from location to location if your rate is going to peter out. And then certainly you need to consider wellbore integrity. And that's particularly the case if you're looking at some of these closed loop concepts. And that's why I'm personally, I'm more in favor of open loop and directly producing and having portability of your conversion system so you can move it from location to location. Basically, this is demonstrating what a closed loop system could do. An insulated concentric internal tubing, and you're pumping down the annulus with cold fluid and producing up the tubing with heated fluid. But it's like any other net present value type of consideration. You need to look at your power production and your power consumption, and make some sort of a judgment and whether or not it makes sense in your situation. And there are a lot of situations where it can make sense. So I figured after 2 days of this, we should show at least one equation, okay? But it turns out there's actually an error in this equation, because I wrote it down and I put in this term right at the front here, this term eta, which is the efficiency, but I'm also talking about thermal energy. So what I want to talk about is electric energy, and eta is the efficiency term, and the efficiency depends on the temperature difference and your flow rate. And you can see that overall, there's a contribution from oil produced, more so from water produced, because the specific heat of water is going to be larger than the specific heat of oil. But there's also a strong dependence on your flow rate and the temperature that you have. And so you can look at this and you can say, well, the efficiency is going to be the controlling factor. I have something where I have maybe the temperature difference and I have maybe the flow rate, but what about the efficiency? Well, what you can see is more and more these days, there are multiple companies that are producing devices that can deal with the low efficiency. And this is particularly accelerated by the development of new refrigerants and new working fluids that really can make a difference. And you can be producing a moderate amount of electricity at relatively low differential temperatures. And this is a list prepared by folks from the University of North Dakota, which have a real background in this area. But this is a couple of years old. And so there are really other opportunities. There's also some nice publications in the literature that look at a structured way of comparing these projects. And I'll just run through these very briefly, but Soldo and Elamati had about 6 or 7 methods for comparing these, looking at the overall power produced, looking at comparing the temperature and the flow rate, coming up with indices where not only do you just look at the temperature of the reservoir and the produced fluid, but you can look at the engineering considerations, including also the outlet temperature and the pumping that's going to be required, parasitic losses, as well as some of the engineering considerations that may be associated with scaling, corrosion, interference, environmental impact, and ultimately, of course, we may have to look at the cost. But this is one of the things that sort of attracted us to this, where there are many, many opportunities in North America as well as in Europe, as I pointed out. Definitely opportunities in Texas, the DJ Basin, and potentially in the foothills of the Western Canadian Sedimentary Basin. I think Will Gosnell from North Dakota said it very well. He said that, look, there's going to be a lot of electrical power is going to be required to produce some of these giant reservoirs. And in terms of the Bakken in particular, the infrastructure is not in place to do that. So the significant improvement in binary power plants, these organic Rankine cycle plants, facilitates using them in some of these large basins. And the last one was prescient, okay? I mean, Gosnell said this in 2019, and we can look at what happened in Texas this past spring. And so there are opportunities to ameliorate weather-based considerations. And so conceptually at EGI, we're considering a project that will look at assessing electrification from some of these waste heat sources. And not only does this entail compilation of heat data, thermal data using conventional geothermal technologies, But it goes on to the third part of this, where we'd like to do a ranking system, that not only in terms of how much heat is available, but does this make sense from an engineering and sort of a generic cost process. Also a project to summarize some of the existing technologies and the opportunities in this area, and some of the heat conversion systems that are available. And we would partner with an engineering company that has a significant amount of experience in this area called the Gray Edge Group. And so there's my timer telling me I'm done, just so that Al doesn't have to chastise me. But I am done, and I'd be happy to take any questions.
So we'll go ahead and turn the time over to Milland here to kind of wrap up our corporate associate conference.
I think these have been two very good days. Hopefully we gave you a good flavor of what EGI is and what it is doing currently and what it has to offer as we move into the future. Let me start with where we actually finished, which is I think it is right now more than just hydrocarbons, right? In the energy business, you have to look at how one would monetize the entire prospect in terms of what you're producing and what your liabilities are. So if carbon is a liability, then you have to figure, and it is, you have to figure out how to dispose of it as you produce it. And at the same time, you might be producing good bit of water that may have minerals in it as well, and heat. So we finished with a couple of discussions on how one may be able to use that heat more effectively. It may add marginal value to your prospect, but these marginal values will keep adding up to where the prospect eventually becomes economical or largely economical. And that's essentially what, I mean, obviously, these things have to be economical for the technologies to take hold and proceed. But as you look at this entire cycle, as we call it, cradle to grave cycle, you need good geologic information. You need good geologic understanding of the subsurface and how this translates to engineering decisions that you make. And again, hopefully we showed you that we have people working at EGI and on campus very collaboratively on all of these aspects: the geologic data generation, interpretation, using different types of data techniques, including machine learning, to take that data as far as it can go. So I think this integration and collaboration is what we wanted to emphasize over the last couple of days, but we were able to show only few things, snapshots of what we are doing. And this is just to get this dialogue going. And I would like to emphasize that this is a dialogue and that we would like to hear from you, continue to interact with you, and then see how we can work collaboratively to create a win-win proposition, a proposition where you have some value to the interactions with EGI and with the University of Utah. So once again, I would like to thank you very much for giving us the time for these last couple of days. And we would like to be in touch